Good morning. Today's lesson builds on everything that we've done so far in the Principles of Computer Science aspect of the course. That's what the P stands for in the P worksheets. The P is mostly topic 2, 3, 4 and 5, and the CT, the computational thinking ones, are topics 1 and 6, the algorithms and programming ones. So logical binary shifts, we need to be able to remember and understand how binary works, and then focus on the easier of the two binary shifts. We've got a logical and we've got an arithmetic. Today we focus on a logical. So if we have a binary integer, that means that we have got zeros and ones that represent whole numbers. We can do a logical shift to the left and a logical shift to the right. We want to work out how to process that, which is dead easy, and how to work out what effect that has, what impact that has on the actual value, which is also quite nice and easy. So we'll go through some examples, but basically you can multiply and divide by powers of 2 by shifting binary values left or right, and we'll look at that. And we might lose some precision after we divide by 2. We'll look at how that works. So multiplication and division are slow processes for a CPU, as in a CPU is very, very fast. It's stupid, but it's fast. It's stupid because it just does the same thing over and over and over again. It can only do a limited number of things. But it's very fast as it can do billions of instructions per second. Addition and subtraction, it can do in one clock tick. But multiplication and division are more complicated for a processor to do. One way that you can speed it up, not by multiplying and dividing by every value, but certainly powers of 2, you can do very quickly just by shifting. And there's two forms of shifts. We'll do arithmetic probably next week. We'll focus on logical today. So what on earth does it mean? Well, so far we've already, let's work through this example on here and talk about what it actually means, because I don't like things that are just there on PowerPoint because you can't really understand. Can I not paste into this new version? That's really irritating. Come on. Where's it gone? It's all the way over there. We've got 3 zeros, 1 0 1 1 1 1. The idea is that all of the ones and zeros just shift across to the left. So where we had 3 zeros at the start, we've now only got 2 zeros at the start. Where there was a 1 at the end, that one's moved across, and we've now got that extra 0. So the idea is for a logical shift, you just pad with zeros. The original value is 23. So why is that? Because, we've got a 1 plus a 2, which is 3, plus a 4, which is 7. We ignore the 8 because it's a 0, plus a 16. So 16 plus 7 is 23. If you shift all of that to the left, then you've got a 2, a 4, an 8, and a 32. Add all those together and you get 46. And it shouldn't be a surprise that shifting left multiplies by 2, because if you remember the placeholder values, you've got 1, 2, 4, 8, 16, etc., etc., etc. All of the values for binary multiply by 2 as you shift across to the left. So it makes sense, doesn't it, that if you have the binary value 2 and you shift it across to the left, that the value is multiplied by 2 because it's shifted across to the left and the place value for each bit multiplies by 2 each time. Okay, so just a reminder that the most significant bit is on the left. Why is it the most significant bit? Because it's worth the most for the bit values. And the least significant bit is always worth 1 on the right. Okay, so we've talked about a logical shift to the left where you multiply by 2. It's very similar for shifting to the right, but you divide by 2. Just like previously, we shifted in a 0 on the right to the least significant bit. If we're shifting right, well, it means that the most significant bit is no longer the most significant bit, so we have to pad it with a 0. So thing to remember from today's lesson, logical shifts, you pad with 0 on the left or the right. So here we've got 23. If we shift it right, divide by 2, well, we don't get 11.5 because, why not? I'll pause the video and we can discuss. The idea is we've got 8 bits here. That most significant bit has become the second most significant bit. That 0 has been shifted across. That 0 has been shifted across. That 1, all of these bits have been shifted across, but this one has just been lost. that was worth 1 and we've lost it. So if we had an extra bit here for a half, it would still be there, but we've lost it. That's what we meant right at the start, where it said we might lose precision because as you're shifting, we've lost some bits. They've overflowed. They've disappeared. So if you want to shift more than once, you're just multiplying by a power of 2 or dividing by a power of 2. So it all depends which direction we go in. So if we are shifting to the left 3 times, as in, come on whiteboard, where have you gone? Super slow computer, there we go. If you've got this number, how many bits have we got? There we go, that looks like an 8-bit number. And we go a logical shift to the left twice, then we're going to lose these 2 bits, and we end up with 1, 1, 1. Why is it drawing arrows? That's really irritating. No, thank you very much. Stupid thing. We might have to just deal with the arrow until I work out how to use this properly. And then 1, 2, 3. And then we've padded in those extra 2 zeros on there. So the effect is we've multiplied by 2 and we've multiplied by 2 again. We've multiplied by 2 squared. If you wanted to go the other direction, let's do this in rainbow twice from the original one, well then we'll have lost 2 zeros on the right and we've had to put 2 zeros on the left. So shifting right divides by 2, shifting left multiplies by 2, and if we're going left twice, we're multiplying by 4. If we're going right twice, we're dividing by 4. Where's the PowerPoint gone? So I think it's time really to get started on the worksheet. Sorry, I've waffled a lot today. Here's how we get started. First of all, use your revision notebooks to help you with this. 11 in binary before the shift. Well, we're going to need a 1. We're going to need a 2. That makes 3. We're going to need a 4. That makes 7. No, we're not. Let's think. We're going to need an 8 and a 4. No, that would make 12. We're going to need a 8. Oh my goodness, I can't do my... Yeah, no, that's right, isn't it? 8, a 2 and a 1. And it should be 8 bits, so 1, 2, 3, 4. And then you've got your binary after your shift. Which way are we going? Shift left once. So we've lost one of the 4 zeros at the start. 1, 0, 1, 1. And we've had to put an extra 0 on the right. And then if you work that out, and I want you to work it out on paper, don't take shortcuts, write out the bit value for each of them. What should that be? Well, it should be 22 because we've multiplied by 2. That's what we want to do here. This is half term 2. This is P8. Find the worksheet. I'll give you your screens back. So for activity 2, we're going the opposite direction. We're doing a logical shift 1 space to the right. So the kind of working out I want to see is the original denary value, in this case, come on computer, you can do this, 11. You'd write down the denary value, oh. Here we go, come on, black, please. Why is it so slow? Windows 11 has changed the whiteboard app and I'm not that impressed with it. Okay, so we've got 11. We need to work out what that is. So we write down the bit values. 1, 2, 4, 8, 16. I know you can do it in your head, but you're likely to make a mistake under pressure in an exam. So always take your time and do it slowly. If you want to try and work out what 11 is, you can make 11 from 8 and 2 to get 10 and 1. Remember, there's only one combination of these values to get any denary value. So that's our initial binary value. That goes in here before the shift. Then we want to shift right by 1 space. So every bit gets moved 1 space. So we get an additional 0 on the right, sorry, on the left, because for a logical shift you always pad with zeros. And then I've got the original 4 zeros, and then 1, 0, 1. Oh, but that one is lost. That's what it means by precision lost. So you'd say, yes, precision is lost here, because we went from 11 down to 5, and the 0.5 has actually been lost of the division. That's what it means. So for the last activity, we're shifting by more than one place. So I'm going to go through this one. So we have an 8-bit binary value, 4 zeros, and then 4 ones. So let's go through what this means. Oh, come on, just go away. 4 zeros, we said, and 4 ones. And it says we need to logical shift left 4 times. So if we shift across once, we're going to have 1, 2, 3, 4, and a 0. That's going to be multiplied by 2. If we shift across again, 1, 2, 3, 4. We've now introduced 2 zeros on the right, and we've only got 2 on the left. So that's shifting left twice. 1, 2, 3, 4. And now we've got 3 zeros on the right and 1 on the left. That's shifting left 3 times. To shift left 4 times, 1, 2, 3, 4, and then 4 zeros. We've ended up with a value that is not 2 times as big, not 4 times as big, not 8 times as big, but is 16 times as big as it was. Have we lost any precision and how do we know? Well, no, we haven't, but I'll pause the video and we can discuss why is that the case. Yeah, good. So we've not lost any of the ones. If we shift again to the left one more time, that would be multiplying by what did we say? 2, 4, 8, 16, by 32. And we'd end up with a 1 that's fallen off. That's a 1, by the way. Sorry, my handwriting's terrible. We've ended up with a 9-bit value, and we can only store 8 bits of them. So we've lost precision, but we call it an overflow. We can't store that bit anymore. So this is like multiplying by 2. This is like multiplying the original value by 4, by 8, and by 16. But something goes horribly wrong here because it's just an overflow error. So at this point, it's not losing precision. It's an overflow error because that 1 has disappeared off. The CPU would detect that, and sometimes you just get a nasty mathematical error. And sometimes these have been known to crash and explode spacecraft because, like, there was a famous example where a rocket, I'll try and find the YouTube video, a rocket went up into the sky. It looked like it was doing fine, but the acceleration data was being stored as a 16-bit value, which was fine as it got up to a certain amount, but then when it got too big to store in a 16-bit value, it overflowed, and then it suddenly thought that the acceleration was much lower than it actually was, and it compensated and the rocket blew up. So you've got to be really careful with this stuff. But the point is, if you shift left twice, it's multiplying by 4. If you shift right 4 times, it's dividing by 2, 4, 8, 16. It's dead simple because all you do is introduce zeros either on the right or zeros on the left. The harder thing to think about, which is your extension today, is what's the limitation of logical shifts? What do they not cope with? And then try and write a Python program which asks you to type in something like this and then uses your string indexing to just get like the first character to the end, concatenated with an extra 0 on the end. So you can do all of this with just string indexing like we did last lesson. Just shift them across left or right. You don't have to finish it, but I'd like you to attempt it if you want the marks for the extension.